Did you honestly think you were going to learn everything there is to know about motion tracking in Blender in only 2 tutorials? Is that honestly really what you thought? Well, no, we're going to need a part 3 and maybe even a part 4 and 5 because today we're talking about camera tracking, which is a big topic by itself. And generally, whenever you're motion tracking in any program like Synthesize, Buju, Blender, of course, 3D Equalizer, your main goal is generally a camera track. And for the people who are like, you keep saying camera track, I have no idea what you're even saying. Basically, the scenario is you're filming some footage with a camera that's maybe moving through a scene, or maybe it's staying still and just panning around on a tripod. It's called a nodal pan. So you have some kind of footage, and what you want to do is using motion tracking techniques, you want to extract camera path information out of that. So you want to use motion tracking to find out how the camera was moving, and the reason for this is that you can add 3D stuff to your scene, you can manipulate the footage and using like projection mapping and all this. So basically the idea of a camera track is to get camera information so that you can do stuff in 3D to your scene. That's the general idea. So let me show you the footage we're working with today. So inside my camera track folder, I have 3 shots since I want to go over this again and again and again because this is kind of the bread and butter of motion tracking. The most important part, we have this footage that I don't need volume for. And in this case, we're just moving through a scene. The camera is physically moving through space and we want to extract the path from that. In this next shot, you can see that it was out of focus to begin with, but I already turned these into image sequences, which is something we talked about. Make sure you watch the earlier tutorials. So I cut this out of the image sequence, this part right here, and also trimmed the ending a bit too, probably. So in this case, we have the same kind of idea, camera moving through space, but we have very clearly defined geometry of our scene. We have a floor and a wall, and the wall has, you know, kind of this, it's not an indent, it's a extrusion. But generally, it's just 2 surfaces here. And then finally, once this finishes playing, we have this shot right here. And it's kind of hard to tell if you haven't had a lot of experience with this before, but this is what's called a nodal pan shot or a tripod shot, meaning the camera's locked in one place and is just tilting around like this. I like to use the word nodal pan because tripod just implies on a tripod facing forwards. So nodal pan just means it's on a node and it's panning around like this. And this is kind of the same kind of methods to use to get a camera solve out of this, the tripod shot, but you do something a little bit differently because since your camera isn't moving through space, you can't really get any depth information. But of course, none of this means anything until we start talking about how to actually do this. So let's open up Blender, and you can see we're actually using the release candidate, which is a big deal because a couple days ago this didn't even exist, and Blender 2.8 stable is coming out very soon. This is the final kind of piece of the beta. For the people watching it in the future, you're like, oh, you know, 2.9 is already out. What are you even talking about? So we need to set up our project the same way we've been talking about over and over and over again. So make sure you've seen part 1 and part 2. First thing we need to do is make sure in the render tab under color management, we have our view transform set to standard. Again, this is going to make sure our footage looks, or our image sequence is going to look as we expect. It's not going to alter the colors using filmic mode or anything like that. And then the second thing is we want our desired frame rate, which again is 30 frames per second, at least in my case. If you filmed 60 FPS and turned it into an image sequence, 60 frames per second. 30. I just talked about it and had trouble finding it. So I think that's pretty much all the setup we need to do. Maybe also save our scene, call this part 3. Okay, now we've set up and we need to go to the movie clip editor, which is where we do our tracking. And then let's open up the shot. So inside our tracking folder, we have shot 1 sequence, A to select everything, and import. And I've also developed some new technology, by the way. Hopefully this works. If I do this, it should change where my camera is. Hopefully it's actually doing something, or else that's a lot of nonsense. I guess I can check. Yeah, that is working technology. So just in case something appears behind my head, I could just, and look at that, everything is solved. So, okay, so we have our shot in here. We want to make sure that our project settings are matched up. Right now our endpoint end frame is 250, so set scene frames does exactly what we talked about, so 1 to 176, and let's load this into memory with prefetch. Okay, so now everything's in memory. We can play this. It's playing crispy smooth, butter smooth. I don't know what crispy smooth even means. And this is a good time to talk about what we even want to track. So again, the idea of camera tracking, the way we even get that camera path to begin with, that motion path, is we're going to do a bunch of 2D tracks from a bunch of different spots in our footage, and they're all going to move a little bit differently relative to each other. So for example, if we track some feature, some dot on the sidewalk here, versus let's say this dot on the car, since they're in different depths in the shot, their X motion's not going to be the same, nor their Y motion. If we pick two spots that are close to each other, like for example this and this, they're going to have pretty much the same motion since they're locally very local and they're on the same surface. So this kind of theory kind of tells us what we want to be tracking. We don't want to track things that are incredibly close to each other since we're not really getting any new data from this. And also we want to track things that are on different surfaces because they behave very differently. And we want to get as many tracks doing different things as possible. And we want those tracks to be very accurate. So even if we can try to track something way off in the background, that's really hard to see if we're getting it right. We don't want to do it. We want only accurate tracks that also last for a long time. So a track that lasts for all the frames, like from 1 to 176, is very valuable to us. And another thing is that, I guess we haven't talked about this before since we've just talked about tracking and the different motion models, we don't want to track objects that are moving. For example, biker dude and phone kid in the background, and maybe this car if it's moving. The reason is it's going to track, but we're getting motion that isn't really representative of the camera moving. Again, we want information about the camera. If we track this person right here, he's going to be moving to the side. The camera isn't moving to the side. So we only want to track stationary features that are far apart, behaving differently, and generally we want to get stuff from all over the frame that are also at different depths. That's the general gist of it. So let's actually lay down some trackers and then keep talking about the theory. So I'm just going to use affine motion model as I talked about. Shearing and deformation is pretty much all we need. We might hop into perspective tracks. We'll see about that. That's the crazy option. We're going to enable normalize, which again makes this tracking invariant to lighting conditions. So especially in the outside scenario where clouds could be going by, shadows are no longer a big deal most of the time when you have normalize applied. And then for our correlation, 0.9 seems to be our magic number, and this is just saying 90% confidence in each match or otherwise terminate tracking. So it's going to track one frame. If it's not 90% confident in a match, it's just not going to do that. It's going to stop. So we're going to get very accurate trackers, which again is very, very important for this. So, for example, we can track something like this dot right here. We'll see if Blender can grab onto that for long enough. So G and then Shift to adjust that. And then Alt-S for our search box that we talked about. And there's a bit of motion in this shot, obviously, nothing huge. So I'm going to make our search box a bit bigger so our pattern area doesn't escape, as we've been talking about. Again, 2D theory is going to be used for 3D results. And then in our track panel, I just want to make sure that's nice and centered. We can move that a little. And then let's lock onto this and Control-T to track forwards. Okay, so that's doing pretty well. And then it stops tracking because this is looking fairly different from the initial first frame, which it's using as reference. So we can just expand our search box to add another reference frame. So from now on, it's going to track and match patterns relative to frame 149. So Control-T. And this made it all the way to the end. This is a perfect tracker. It's accurate, as we saw, and it lasts the whole shot. Control-L to lock this. And the general idea is we're going to need 8 of these. Not the same 8, but we're going to need 8 trackers to exist at any frame in our shot. Ideally, it's the same 8 trackers. So you can tell that this is going to be a lot of tracking. And just something I want to point out that I kept referencing earlier and saying, don't worry about it. It's spoilers, don't worry about it. Is that when we added this, if you go to objects, what's objects? Well, now you're going to learn what objects is. You're going to see we have this camera object and nothing else. And when we added our tracker, it went right into this camera object. So you can think of this as a camera, and then what belongs to this is trackers. Right now, only one tracker. If we add another tracker, we're going to have our camera and then 2 trackers that belong to it. Of course, this is what we want because we want at least 8 trackers on all frames that belong to this camera that we're going to use to extract the camera path out of it. We can also add other objects, but this is object tracking, so don't worry about it. You see our tracker disappeared because nothing belongs to our object, but to our camera, we do have something. Don't worry about this. I'm going to get rid of it. So once this is good, we can just keep tracking. So again, the most important part of this is not how you actually do the tracking, since that's what part 1 and 2. You have 2 hours and 20 minutes of training on just how to track in general. But the theory is, what do you want to track in the first place? So let's add another tracker right here. And the question is, why did I choose this? Well, it's definitely at a different depth. It's further away from the camera. And additionally, it's at a different altitude. So it's in some sense on a different surface. It's not on this planar sidewalk. It's slightly elevated. And in 2D, we have this one, which is right in the middle, and this one's kind of occupying the top left. So we want some distribution in 3D and 2D. And this is just a nice feature with a lot of contrast. It's pretty much like a tracker marker. It's a dot that was built for tracking. Okay, so Control T. That is looking good, and it lasted throughout the whole shot. That's always a good sign. Let's do something here. We'll see if this gets occluded by the curb. So like that, scale this down, and then Control T. And you can tell that at least in an easy shot like this where there isn't a lot of motion blur, it's not going to take that long if we only need 8 of these, but it can get pretty complicated, especially when there isn't a lot of detail in your shot. So again, this is at a different altitude since it's not on the sidewalk, so another good choice. I'm now going to do this car, and it's important that this thing is not moving, right? It's a parked car, otherwise the motion wouldn't be representative of the camera motion, wouldn't represent the camera motion. And another thing is that even though the rest of this car is very reflective, which will make it look like the pattern is moving, even though it's not, it's just the reflection across the surface of the car, this little light or metal thing is probably not going to change at all, so it's going to be fine. And it looks like a circle, so it's a tracker marker. Control T. Okay, and just in case I want to review this tracker, make sure nothing weird happened. That is looking good. It almost made it to the border margin here, but it worked out fine. Again, shift left arrow for first frame, and then shift right arrow for last frame. What else can we do? So for example, this one right here would probably be fine. I would want to make sure that it's not moving in the wind at all. Definitely you do not want to track leaves that are moving in the wind, but maybe the tip of this is going to be fine. So let's track that, and it should work very well with the deformation and all that, although I suspect that this bench might be a problem, so let's try it. Okay, so it made it, except of course it goes out of frame, and we don't want to do any offset tracking or anything we've been talking about because there's no point. We can just pick a new tracker and be on with it. We don't need to really commit ourselves to this one. But it did last for 78 frames, so it is worth keeping. If it's something that lasts for under 10 frames, I wouldn't track it at all. Control L and keep going. Okay, now ideally I would like to get something on this tree, but I don't think there's enough detail to grab onto. We can try though. It's at a very different depth and altitude, so it would be a great tracker. Okay, let's see how that did. Looking at this area right here, there's a lot of noise, and to be honest, I'm not quite sure if it's the exact right spot. We want to minimize error because any error that we get is going to accumulate because it's using all these trackers to calculate for our camera. So one weak link can ruin everything. Okay, let's do a save and keep tracking. We can pick another thing on the sidewalk. As long as not everything is on the sidewalk, so we have some different altitude, we're going to be fine. Okay, L for lock, or for centering, and then Control T. That worked perfectly, and let's get a couple more. We could try something in the distance. I'm not very confident that it's going to work. Maybe something like, a lot of this is overexposed, not a lot of detail in here. we could try this pull over here. And again, the reason we're doing a whole part 3 for this is very important in the workflow of any VFX artist, so I'm really focusing in on this one. So Control T, let's see how this does. That did horribly, but did it hold on for a while? Held on until here. You could cut it off here, again, track and then clear to the right, and then you could lock this, but again, I wouldn't recommend keeping a track like this, so let's just delete it. We want very accurate results, and luckily for us, we have a lot of dots all over our scene. So locally, we don't want it to be very local. I don't even know what that sentence means. So let's pick this right here instead of a dot right here. And then track that forwards with Control T. Lock that in, and then how many do we have so far? So it looks like we have about 6 trackers that last the whole shot, and then I know this one only makes it halfway through. We can also go to the last frame and then pick something that's in here and track backwards. That's always a good strategy. So let's pick something in this brick area, like this little, I feel like this one has more contrast. Basically, if your eye can follow it, then the algorithm should definitely be able, and by algorithm, I don't mean YouTube algorithm, I mean Blender tracking algorithm should be able to follow it. So Shift, Control T, or of course hit this button right here. Shift, Control T. Couldn't even see that, it was moving so wildly. Okay, yeah, I think that is good. It's a shame it only made it about halfway backwards, but Control L to lock. And let's get a couple more down. We could try this area. That's kind of the intersection of a bunch of different lines. And you know what, for this one, let's do a perspective track, just because the affine motion model isn't the best for everything, and this is really a perspective scenario. We're moving further away, and you can see this plane is just going to be shifting like this, kind of, if you can imagine that motion in your head. So inside the tracking settings, we want to change this to perspective, and somebody asked me in the comments, I thought I clarified this, but I'll say it again. The motion model here is saying when I add a tracker, I want it to inherit these properties. And these settings are local to the tracker. So this one set to perspective. If I hit this one right here, it's affine. So it's on a local per tracker level. So let's scale this up with a little less search box, and then Shift Control T. Ideally, we start this on the first frame, because like I said, for some reason tracking backwards takes a bit longer. I don't know, I didn't design it. Camera tracking can be seen as very boring, can also be seen as very relaxing. This is one of those things, just like retopology, that you want to be listening to a podcast for while you're doing it. It's not very entertaining to just focus all your energy on it, unless you're watching this video. Then you want to focus 100%. Okay, so let's see this. Again, we would just want to focus on the center point. We don't care about these 4 corner pin type things. We only care about the X and Y data here. And by the way, because I haven't been mentioning this, if we open up this window for a movie clip editor and load in the same footage as before with graph, you can see, I think this is the first time we have multiple different splines, graph, I don't know why I called it a spline. We have multiple different graphs on the same graph, right? We have multiple different data sets on the same graph. Each one is of course representing a tracker. And when we select them, you see it's going to select each individual graphical representation of that tracker. And generally, you see they pretty much clump together. There's a bit of variation, but they clump together. And that variation, let's say this one right here has a lot of variation, you can see that it is the car tracker. So of course it's going to behave very differently on the X and Y because it's kind of not attached in terms of geometry to this stuff over here. So you can expect different types of motion. If we were again to track the biker, we wouldn't want to do this, but if we did, we'd expect wildly different stuff. So as long as this stuff is pretty packed together in a normal way, if you see anything abnormal, like for example, this right here, I don't know why that's happening. It could be, in that case, because you're getting some inaccuracies around the margins as it gets out of frame, so that's something we want to look out for. But for now, we're just going to ignore that. Very soon, we're going to need to really care about these graphs. So I think we need one or two more that last throughout the whole shot. What can we grab onto? Something here. So there's a lot of white dots. Yep, we're back in affine. So let's control click and then pick that, control T. Did that make it all the way through? No, we had some, I don't know if it was motion blur issues. I don't think so. I think we just need to make our search box bigger, and let's keep tracking. There we go, made it all the way through. Sometimes that's all it really takes. Okay. Is that all we need? You know what? I do see this nice looking, I don't know what that is, stick. Either way, we're going to track it. Doesn't really matter as long as we can tell that this would be a good tracker marker. Doesn't really matter what it is. Actually, I do know what it is, but YouTube looks through the words you say and recommends videos depending on those words. So if you say a certain word, it actually becomes less discoverable. So you know what it is. I know what it is. Leave it at that. Okay, Control T. Made it most of the way through. Make that search box bigger. You see the pattern area is going to escape that in the next frame. So Control T. Okay. I think we can squeeze another frame or two. So what we can do is, again, we can reset this because the only thing that matters is the center point, and this is just going to add a new reference frame for us to track. So Alt right arrow to go frame by frame. Okay, so we got 2 or 3 extra frames out of this, which is worth it. Control L. So in the beginning, we definitely have 8 trackers. What about the end? Okay. So Blender will tell us if we have any issues with having 8 trackers on at all times, but we can also do a manual review of this. And it does look like there are 8 at all times, so let's try to follow through with this. Okay, so we have all our trackers, and now what we want to do is combine that data, all those tiny variations, even though they're kind of all moving together because it's all being affected by one camera motion. We want to take that and create a camera path. So we go over to this solve panel, which we've only gone to for plane track, I believe. So most of this is pretty new, and there's a lot to talk about. So the first thing you're going to see is this tripod checkbox. And if we read the description, use special solver to track a stable camera position such as a tripod. You want to enable this if your shot is a nodal pan like we talked about, still camera but just panning around, or if you're filming stuff that is way, way into distance, like incredibly far, you're on a boat and filming an island or whatever, and you're moving your camera through space, effectively you're not, because it's so far away it can't tell any depth changes, so that would also be considered a tripod shot. That's just a special case. Keyframe is the next checkbox, and this is something we want to enable. Automatically select keyframes when solving camera object motion. So this takes some explanation, along with keyframe A and keyframe B. The way I think every camera solver in other programs too works is you give it a part of the footage. So it's not looking at the whole thing. You just give it a part of the footage that you say, I want you to look at this specifically. It's going to use a whole bunch of different math and algorithms to get a camera solve just for that tiny area. It's going to give us a camera path. And then what it's going to do is using that, it's going to extrapolate to all the other frames. So there's kind of an art to choosing a good keyframe A and keyframe B. That's the small range that it's going to calculate, and then it's going to reconstruct and extrapolate everything else. So what you can do is pick a number here, and solve, and you're going to get some kind of result, and you just keep tweaking this until you get the best result possible. Or what you can do is enable this checkbox, and it's automatically going to find a good pair of keyframe A and keyframe B. I don't know if it's guaranteed to find you the best one, but it gets you a good one generally most of the time. So what we're going to do is with keyframe enabled and with refined set to nothing, we'll change this later, is click this big solve camera motion button. And we'll see if it works. Okay, so something happened. We don't really know what, but something happened, and you see we get this solve error of 1.059. This number you're going to grow to hate or love if you're very good at camera tracking. This is the most important value you want to look at to tell if you have a good camera track. Again, the same way that when you're tracking a point, it's going to be pretty much on there, but it might be a pixel off, you know, in any direction. This is a measure of how good your camera solve is. So obviously you want this error to be 0. You want it to be as small as possible. So you need to know if you have no experience with this, what's a good value, what's a horrible value. If you get something under 3, that means it's pretty, I won't say accurately, it means it's getting the general idea of your camera motion if it's under 3. If it's under 1, you're now getting into acceptable territory. So here we're just about at 1, so this is acceptable. If we're under 0.5, now you have a good solve. Anything other than that, not that good. And if you get something like 100, a lot of the times you're going to hit this button and get something like 100, 50, 200. In this case, we picked very good trackers. So we basically helped the camera solve, right? The worse the trackers are, the worse results you're going to get. So you want to get this number under 2 to begin with, or under 3, and then you want to narrow it down to 0.5, and we'll talk about how to do that. So again, if we go to this movie clip editor, you're going to see a new color. We had red, we had green, and now we have blue. And this blue new graph is representing this camera solve. And what you're going to notice is as this number drops smaller and smaller and smaller, closer to 0, this line will flatten out. And that's generally what we want to happen. And you're going to notice that we're getting a bit of waviness, a bit of oscillation anywhere that there's a lot of motion. And you can tell there's a lot of motion because we have a lot of change in the green, which is the Y, so the trackers are moving a lot on the Y and the X. And you can see it's very stable, very flat around these areas that are less chaotic. So ideally, we want to tweak our solve until we're getting something that's perfectly flat. That's the end goal. So before we even talk about how to reduce this error, 2 things need to happen. I need to drink water, that's 1. And second of all, we need to talk about what this error even means. It's 1. What does that even mean? Okay, so here is basically the explanation for all of this. So this would be a good opportunity for me to switch to bottom cam. Hopefully, did that work? Does work. Perfect. So in clip display, we're gonna disable our footage so we can only see our trackers. I was debating this because I didn't know if it would be easier or harder to see what I'm about to show you. But we're also, more importantly, going to enable info, and we're going to enable 3D markers. Okay, and we can disable this lock. So with this info, you're going to see that each tracker has a name. So this is track number 6. We can see that over here, track number 6. And I think at this point I can bring... Did that bring it up? It did. Sorry that I keep checking, guys. I'm a bit paranoid about it. Okay, so you can see that it has the name of the tracker, its average error, and the fact that it's locked, and each one of these is going to have a different average error. So obviously the tracks with lower error, or average error, are very good. So how do you actually measure the error on an individual level? So you're going to see that when we enabled 3D markers, we get this green dot, and this is a bit hard to explain, so I'm going to do my very best. These trackers that we've been dealing with, just the normal trackers where I'm always like, look at the center point, this is the only thing that matters. This is a 2D location on the footage, represented by this red and green X and Y data. Right, that's the 2D location, and this green dot is kind of the projection, the 2D projection of a 3D point. So all you need to know is that a tracker, what we've been used to, is a 2D point, and this corresponding green dot is a 3D point. You can see that when we zoom in very close, there's a bit of distance between them. They're not overlapping. Which means that when our camera solve got its solution, it's doing its very best to make sure that every 2D and 3D point are perfectly overlapping, because that means we got a perfect match. Of course, you're not going to get this perfection, because there's tiny bits of error, there's noise in the footage. So it basically tries to find the best solution that's closest to all of them. And this average error on a per tracker level, so this has an average error of 0.785, is measuring the average distance in pixels, pretty sure in pixels, between these two. So an error of 0 means that there's 0 pixels between them, they're perfectly overlapping. And something like, let's find a tracker with the highest error. So this has 1.3, that's a lot. Anything worse than 1.3? 1.4. I think this is our worst. So on average, doesn't mean on every frame, but on average, these 2 points, this 3D point and our 2D point, are going to be very far apart, which means that our camera solve isn't perfectly matched to this data. It's not perfectly constrained to it. And you can see that there's actually a bit more distance. It's actually visible. So when I say that we want this number to be as small as possible, this number is the average of these averages. So each one has an average error, and then you combine all of those to get this average solve error. So when I say we want this to be as small as possible, that means we want our 3D points to overlap on all our trackers as much as possible with our 2D points. And the better the trackers are, the better solve error you get. But of course there are ways to drop this even lower. So hopefully that was a good explanation for all that. Okay, so how do we drop this even lower? Oh, and by the way, if you don't know how I did this, N for this menu, T for this menu, same as in the 3D viewport. For example, if you go to this animation, N, T, same type of deal. So how do we lower this without adding or subtracting more trackers? There are a lot of methods. The first one, which might not necessarily work, but if it doesn't work, you can just undo it, so let's save. We want to look at these graphs and see if there's anything abnormal going on. And we talked about this before. Just the fact that this is very off from the rest of these is just because it's tracking the car and not this area over here. So not that type of error, but something that just does not look right, and there might not be any, to be honest. It will be very obvious if there are. Okay, so let's just do a test. This might not do anything. So let's say that we like this, except for the very end it seems to have some very weird behavior. Again, that's this right here. What we want to do is cut it off a bit early. So we're going to use this button right here, which we talked about. It just clears everything to the right of this frame. So let's clear it, so we get rid of that little tail, and we can solve again using this new data set. It's only slightly altered, and see if anything changes. So we're going to disable this checkbox, which means it's not going to try to find a new combination of keyframes that, again, it's going to reconstruct from. We're going to keep it on 1 and 43. So now when we hit this button, the only difference we're going to see, unless something horrible happens, the only difference we're going to see is because of this tiny change we made. So let's see. Might not be any different. Okay, so before, let's see, before we had 1.059, we deleted this little tail, solved again, and now we have something that's just barely lower. But it did help, because now we have a smaller pixel solve error, which means on average everything's overlapping more nicely, so that did help. But because there isn't much of these to actually account for, this isn't going to be very good. So the next thing we need to do, and this is by far more important than what I'm about to tell you, is we need to give Blender as much information as possible about our camera. So for example, did we film with an iPhone? Did we film with one of those red Epic cameras that are like $20,000? Did we film with a DSLR? It's important because we need to tell Blender what lens we were using, how the sensor worked. All of this stuff tells us information about the camera that can explain this tracker motion we're seeing here. Okay, so let me get a bit of water and I'll explain this. So generally, especially if you download footage, you don't know a lot of the details about your camera. In my case, I actually don't know most of the details either. So we can see what we can actually recover, is what I'm trying to say. So if we go into this camera tab, you're going to see a whole bunch of stuff. So sensor width, pixel aspect, optical center, also in the lens we have a whole bunch of stuff. We want to fill in as much of this that we actually know because, we filmed it. Do we know the focal length, how much we're zoomed in? Do we know the sensor width, the size of the sensor inside the camera? Do we know the optical center? This one's a bit confusing. Basically, your lens is a bunch of pieces of glass, and if you think of light as a cone coming in or out of the lens, it's not perfectly centered the way you'd like it to be. It's a bit off sometimes, which means that focal length is measured based off this ray. If you don't care, it's not that important. There's automatic ways to account for this, but just know that optical center is saying where is if you take light and shoot it out of your lens, where is the center of that going? That's all that means. And right now it's set to these numbers because our footage is 1920 by 1080. Well, look at this. 1920 divided by 2 gives us the same number. 1080 divided by 2 gives us the same number. So by default, it's saying it's the center of the footage. That's what is a reasonable guess. It's only going to be a bit off from that, depending on how bad your camera is, or your lens is. If your lens is really bad, it's going to be very off-center. Okay, so if you know some of this, great. If you know what camera you used, you can use one of these presets. So for example, you could, say, it's a iPhone. Right here, you could click it and it will automatically change some settings. And there's actually a good chance if you're using a pretty mainstream camera that it will be here, but we're going to assume that we don't know what it is. So none of these presets work. Okay, so how would we actually figure something like this out? So the first and most important value is the focal length. Again, how zoomed in are you? So you can change the focal length on your lens to zoom in and out. So something like a 60 millimeter means very zoomed in. Something like 5 millimeters is like GoPro wide angle. Well, basically, if we change this value and solve again, if this number drops, it's most likely more accurate because by changing our focal length, we got something that's more accurate, or we got to solve that more accurately represents our camera motion. So it must be that the focal length is closer to the true focal length. What I'm saying is we change the focal length, experiment, and see if it reduces our solve error. So for example, we can change this to 25. Solve again. Again, we're going to turn off keyframe so it keeps the same keyframe A and B. And it got a lot better, 0.75. So we're definitely headed in the right direction. Let's keep increasing. Keep increasing. It could only get worse or better. 26. Okay, that got even better. 0.59. Again, under 0.5, you have a very good camera solve. Under 0.1, spectacular. You're not going to get under 0.1. Okay, let's try 27 and solve that. Okay. So now we are getting into worse territory. I'm sorry about my voice. I'm probably going to have to stop recording in a bit and come back because my voice is going. Okay, so this was actually worse, which means we need to go back in the other direction. So 26.5. Okay, it's getting slightly better. You get the idea. So instead of playing this hot and cold game, where hot means you're getting better and better and better, cold means you're getting further away, what we want to do is automate this. And that is in the refine option, so we can have it refine for focal length. And just like keyframe, enabling this found the best, or one of the best, pairings of keyframe A and B that gave us a low solve error. Refining for focal length is going to try a whole bunch of different focal lengths and give us one that gives a good result. So let's save and do this. Okay, so it seems like the best one was around where we were, 26.14. So we got a solve error of 0.5898, which is much better than our initial like 1.05. That almost halved it. So that is a substantial upgrade. Okay, so what's the next thing we can modify? Well, we can change the optical center, like we talked about. Another thing we can change is the lens distortion. If you're using a GoPro, you're gonna wanna listen in on this one, because lens distortion, if you didn't know, is how much your image is being curved and distorted based on the shape of your lens. So as you know, a GoPro has this widescreen, very iconic fisheye lens kind of look to it, where there's a lot of lens distortion. And for example, if we have a tracker near the edge of the frame, like this one right here, its motion isn't going to be very accurate because a lot of that's going to be because of the curvature of the image. It's a flat image, but it's kind of curving where it shouldn't be. And a way to tell if you actually have lens distortion is, let's say you have a straight line in real life. So if you look at this, if you go outside and look at the street, from here, this point to this point, this line is straight in real life. But if we look at it here, maybe it's slightly curved. And that's saying there's some lens distortion, and we need to undistort it so that it straightens out. So you can change your K1, K2, and K3 values to do this. That's basically defining different types of curvature. So you can have fisheye distortion, barrel distortion. They're basically different types of concavity. I wouldn't adjust these by yourself. Instead, we are done with focal length, so now we can only adjust K1 and K2, which are the main two types of distortions. K3 is negligible, and I think Synthesize lets you do K4, K5. very, very negligible. Okay, so let's see if we get a better solve. So 0.5898, and now we're down to 0.5586. Okay, so we didn't see anything happen. We know it found some lens distortion, right? We have some K1 and K2 values. How do we actually see that it calculated lens distortion? Well, what we can do, moving my camera down, is that inside clip display, we can enable render undistorted. It's very subtle, but I'm going to toggle this on and off, and I want you to look at this footage over here. So you can see that it's kind of unbending the image. So render undistorted is showing us the undistorted image. It got rid of the lens distortion. And when it accounts for this, of course, it's going to give us a lower solve error. Okay, so the last thing we can do is, again, optical center. And this one sometimes breaks a camera solve. Sometimes it improves it a lot. So we're going to do it. If it doesn't work, it doesn't work. So actually what I'm going to do is I'm going to undo our lens distortion. So at this point, we got back to our solve error without accounting for lens distortion. And in our refine, we are going to do all four. So we already have our focal length set, but maybe you can find something a tiny bit better. So this is focal length, optical center, K1 and K2. Hopefully it doesn't break our solve, but let's see. And there you go. So it changed our optical center very slightly. So from 960 to 974, and from 540 to 50 about 9, right? So change this a bit, and now we have a solve error of 0.3624. This is fine. This is a great camera solve. Can we do better? We can do better. So I'm going to show you kind of the final trick up your sleeve, up my sleeve, up our sleeves once I teach you, that will make our camera solve much lower. And again, very tedious process, but totally worth it because you're not going to get any kind of drifting when you put a 3D object in your scene. The higher the pixel error, essentially that's not very accurately, but in some sense representing how much you're going to be drifting, right? If you put a cube in your scene, how much does it look like it's there versus how much does it look like it's sliding on the floor a little because everything isn't matched. Tedious process, totally necessary. Okay, so like we talked about, we have, where is it? We already have info enabled. So if we only look at our trackers, we again know what the average error of each of these are. And again, now each of these are now smaller than what we had before. Initially, some of these were like 1.4, but because of all our refining, now we're down to like 0.48 and stuff like this. But again, just like last time, you're going to notice that some trackers are worse than others. This tracker right here has an average error of 0.172. This is very, very good. Whereas something like, what is the worst offender here? Is it 0.4? It's 0.483, I think. So this is by far the tracker that is contributing the highest amount of error to our average, right? Again, solve error accounts for all of these, so one weak link can ruin the whole batch. So what we want to do is take the influence of this and bring it down. So it's still accounted for, right? It's still a tracker here, but it's not contributing as much to this weighted average. The same way that in stabilization we could have it stabilized to multiple trackers with different influences, that's the same thing we're going to do here. So with this tracker selected, you're going to notice that, like stab weight, which is what we talked about before, this is the 2D influence, we have weight, which is the 3D influence. You guessed it. So if we bring this down, something like 0.5, we're saying that we want this to have half as much influence as everything else here. So let me ask you, what do you expect is going to happen when we solve again? When we took the thing with the highest error and said, you know what, don't contribute as much. Most likely, again, I think it's guaranteed, most likely it's going to drop the error. So 0.3624, we're not refining anything, we don't have keyframe enabled, so we're just taking this and only changing this one thing and solving again. 0.33. So initially, 0.36, now we're down to 0.33. And it basically recalculated the error on all of these, but generally made all of them slightly lower. So now this is the worst offender. You want to bring this down, maybe halfway. Okay, now we're down to 0.31. And you can play this game over and over and over again. but you do not want to get to the point where all of these have weights of around 0, because now, yes, you have gotten a low solve error, but is it even representative of your shot in the first place? So you need to balance this idea of lowering your solve error, but staying true to the tracking information you got. So that is something you want to consider. But now, we talked about this before, we have this blue line, which again is representing our camera solve, which was kind of waving around much more wildly than it is now. Again, notice that we need to look this far zoomed out to see the amplitude, you know, the top, bottom, the size of this red X graph. And from this vantage point, this looks very, very flat. Again, you're going to get the most amount of oscillation when your trackers are moving the most. But you can see this has flattened out. We have a much better camera solve. And I think at this point, you could go crazy. Again, you could try to get this below 0.2, and I'm sure you can if you put in enough work. You can also add in new trackers and replace them for trackers that maybe aren't the greatest. Let me try to close Blender. Let me just, there we go. Again, it's a nitpicking, but I don't like that you can't grab windows that easily. By the way, where's my camera right now? Need to get it on the top right. No. There we go. Is that, I will get used to this. I'm sorry, I'll add a little indicator so that I don't have to keep checking. But, okay, so now we're happy with our solve error, and we're going to say that this is done. There's no more refining that needs to happen here. 0.3138 is a great average reprojection solve error. It's a very good result. So what we want to do is, now that we've basically calculated our camera path, how do we use this inside the 3D viewport to, you know, add objects to our scene and do whatever with? So let's talk about that. So we've put in a lot of work, and some people could say a lot of labor, into getting this camera solve with a very low solve error of 0.3138, which again is a very, very good solve error. So before we bring this into the 3D viewport, again, I just want to review what it is we actually did here. So we had a lot of 2D trackers, each with its own X and Y data, and then we used Blender's magic algorithms to basically take all those variations in all the trackers. Again, we need 8 trackers for every frame at least. We used Blender's magic algorithms to extract 3D information from that, and now we should have a camera path. So we have a camera that is matching the motion of the real-world camera that filmed this footage. So basically the question is, how do we take this camera and bring it into our 3D viewport so we can add things into the scene? And it turns out that it's very, very easy. It's actually one button click easy. So before we click the magic button, I'll keep you waiting, is we want to open up, what we want to do is open up the 3D viewport. And by default, we have the default scene. We have our cube, our light, our camera, and ideally we want this camera right here to be the one that is moving. We don't want to add anything else. And again, to do all this, it's just a one button click solution, and that button is Setup Tracking Scene. You click it, and then you see that a bunch of things happened. First of all, we have this plane added, and it's in a new collection, and in fact it's in a new render layer. If you go to now we have something called background. So we're going to deal with that. That's actually not what we want, but it's also isolated to its own collection. So that's one thing. But then much more importantly, we have this camera with these, what look like our tracker markers. You see we have this one over here in the distance, which should be the one that is on this car. So you might guess that these are basically the 3D representations corresponding to our trackers. And that is the case. And if we play with spacebar, you can see that this camera is very slightly moving. It's more obvious when we go into the camera view, which also automatically has our background image sequence added to it. So if we play this, it's going to be very slow, mostly because we have this movie clip editor open. So for now, we can close it. We're probably going to need it again, though. So you can see we have something that kind of looks like it's tracked on, kind of looks like this plane is hovering and drifting above the sidewalk, which is why everything isn't lining up. Again, we can see a lot of, we can see a lot of sliding if we focus on this point right here. That is definitely a lot of sliding. And of course, the reason for that is these trackers, which we know most of them are on the sidewalk except for a couple of them, are supposed to be on the floor, yet they're hovering above, which is why the plane doesn't look like it's sticking on. Instead, if we bring this down and all that, it should look much better. And this is an issue of what's called orientation in match moving. So there's motion tracking, and then match moving is, the branch of motion tracking that usually deals with 3D stuff. Not always, but now we're dealing with match moving. We're dealing with the big boy operations here. So again, this is an issue of orientation, and we can fix this manually by moving everything down or doing it automatically. I'm going to start off by first doing the manual approach, just so you know what's going on here, and then we're going to switch everything up by doing the automatic approach, which is much better and faster in most cases. So in the side view, we want to bring some of these down, or I guess everything down. So it's basically on the floor, and you can see that there's still some variation here that I don't want. I want everything to be on the floor. That should be on the floor. So now let's go to this side view. We can also bring this to the side so our cube is centered, and we also want to rotate until everything's pretty much flat, and then bring this down again. In the side view, we can do more adjustment. And again, it's very hard to tell if we're doing something correct here, because manual isn't the best way to go. Something we can do to help us is these empties. They're not really empties if you look at the outliner here. Now you should be able to see it if I moved my head. This outliner doesn't have any empties. It has our camera, which has a constraint for camera solver, but it doesn't actually have any empties. So in this menu, let's go back. In this menu right here, we should be able to take the size of these tracks and bring them down, just so they're a bit smaller, which makes our orientation adjustment much easier. And I'm thinking we need to rotate this a bit more and bring it up. And what we can also do, if we go into the camera view, it looks pretty much correct. Like the plane looks like it's on the same horizon as this sidewalk, although everything looks pretty big. And I'm pretty sure we should just be able to scale this. And ideally, we want to, we can just scale this, which again, everything is still left on the floor, but we also need to, I guess everything isn't left on the floor, but we also need to adjust everything again. So you can tell that this process is very time consuming, but now our plane is smaller, and it actually looks like it's doing a fairly good job of staying where it's supposed to be with minimal drifting. If we zoom in here, you can see this is much better than what we had before. Still a bit of drifting because it's not perfect, but not a big deal. So that's manual orientation, not what I recommend. So let's open up the movie clip editor in a new window and have that set to our clip. And you can see that in the solve panel, we have a orientation menu just for this. We have a whole bunch of operations dedicated to making sure that our floor is where it's supposed to be. So the way we want to do this is select 3 trackers that are on the floor. Of course, we need to define what that even means. So we can have our floor be the sidewalk. We can have it be this tiny dirt hill over here. So we can pick what altitude the floor is at. It can even be on the street. But of course, we're going to pick the sidewalk. So 1, shift-click 2, shift-click 3 trackers, which define a triangle if you were to triangulate these. And we want this polygon that would be made to be resting on the floor. So with these 3 selected, all you want to do is hit this floor operation, which you can see moved our camera. And if we go into our camera, now everything is pretty much lined up. It's not a perfect solution because you're perfectly relying on the 3D positions corresponding to these trackers. And if they're not very accurate, then you're not going to get a good orientation. So we could also pick 1, 2, 3, which is a different selection since we didn't pick this one, run another floor operation, and you're going to get something a bit different. Is it better? Well, it depends on which trackers you chose, really. So that's one thing we can do, and that's one axis of freedom taken away. So now we have our plane on the floor, but we can still slide around this plane and it will still be on the floor. We can rotate it. So we want to keep narrowing down these axes of freedom until we get what we want. So we want to perfectly constrain this. So the first thing I want to deal with is sliding this around. Where's the center of the plane? Well, we can pick a tracker like this one, say this is the origin, and then all we have to do is set origin. And now you see everything has slid, there's a word for this. It moved or translated around, but of course the plane isn't what moved, it's the camera. So if we undo this, and now we set origin again, you can see the camera is what's moving, giving the illusion that the plane's moving. Very important idea. Okay, so now we have a plane on the floor, we translated it to where we want, but we can still rotate it and everything's still meeting our conditions. So to rotate, we can say we have an origin specified, So we can say this this tracker relative to the origin will define an axis. So we can say that the line between this tracker and the origin can be something like the x-axis or the y-axis. And I'm going to go for set y-axis. And you can see that now our y-axis is going in the exact same direction defined by these two trackers. We can also make it the x-axis, which flips everything by 90 degrees. So it's pretty much the same thing. The last thing we can do, and already we have this fine, but let's just play around with this, is we can choose how far away the camera is. So basically how zoomed in it is. By picking two trackers, we can say what is the number of units between these two trackers. So if we have these two trackers, and we have a distance of 1 over here, and we set scale, you see that everything becomes very, very big, and really that just means the camera got very, very close, because we said that there's only 1 unit between these. Instead, if we pick something like 5, which is many more units, and set scale, now our camera moved away, and now everything is looking much smaller. If we get ridiculous, like 15, you can see everything is very, very small. But let's go back to 5. And again, you can do the same type of thing with orientation by just doing a wall operation, which you can tell is basically the same thing, but, you know, flipped up by 90 degrees. Now we're talking about a wall instead of a floor. This is definitely a floor-based scenario, but you could totally see yourself tracking a wall and needing to use that kind of operation. Okay, so now we have everything oriented correctly. So I'm going to close this, and then in our camera properties, we can take our background image and make it opaque by bringing up our alpha to 1, which is 100%. So now we can see everything, and if we play this, this is a very good solve, and it should be, because we have a very low solve error, we have our orientation done correctly, so everything should look like it's sticking on fairly accurately. And if we wanted to, we can do some last-minute adjustments. I don't think we're going to need it. That's looking fine. What about this view? This could be rotated a little, so I'm just going to rotate a tiny bit. See how that looks in the camera? Yeah, it still looks like everything's sticking on, so you could spend a lot of time with this, but let's say that we're done with this step and we want to start adding 3D objects to our scene. Of course, we already have a plane and a cube, but let's talk about exactly what's happening here. So in the rendered view, we are currently in Eevee, so in the render tab, let's save. We want to switch over to cycles. You can see some weird stuff is going on. First of all, you can see that this plane is gray, and that's because it's a shadow catcher. If we go into the properties here, I believe it's in here, and then in visibility, you can see that shadow catcher is enabled. If we disable it, it's just black. So this is a shadow catcher, which means it's a transparent object, but it still keeps the shadows on it, hence the name shadow catcher. If we go into the render tab and enable film and then transparent, you can see that this is actually indeed transparent. And I don't know if this is a bug with the release candidate, because just like one version earlier, you could actually see the background through this, but just imagine that the background image is actually being shown through this shadow catcher. So this could just be a temporary bug, not a big deal. So let's delete this cube, which is cut in half by the shadow catcher. We can see the bottom by going under the shadow catcher, so it's transparent, doesn't show objects through it, and supposedly holds shadows even though we can't see any. But we'll deal with that. So I'm going to delete this cube and pick something more interesting, like a monkey. It's probably the standard example. And we just want to bring this and rotate it so it's sitting, whoops, let's go back to rendered view. So it's sitting on top of the shadow catcher. Sorry I'm stuttering so much. This is pretty much the first time I talked today. I took a 1-day break from recording because my throat was dying. But hopefully I'm doing okay here. Hopefully you really understand what we're getting at. So now we have this monkey, this Suzanne. We can actually make it a bit smoother by adding a subsurf. And yeah, that should be good. We'll apply it and then enable shade smooth, so everything looks nice and smooth. Okay, so we have our monkey, but where is the shadow? And this is the issue I was talking about earlier, where this ground plane is in a different collection in a different render layer, which means that right now we're only viewing the foreground. If we go to the background, there's our shadow. It's separated, and this might be something that you want. Why is this set up by default when you hit Setup Tracking Scene? Well, when we go to the compositor, again, we already talked a lot about compositing. you can see we have two render layers nodes, one for the background and then one for the foreground. And the advantage of separating these is, for example, we could add a hue saturation value and put it here. So now we'd only be affecting the color and value and saturation of the shadow. So we've separated the two of these. In this case, that's actually not what we want, but just so you know, there is a reason for this. So we're going to delete this and the background node. And let's talk about what we have so far. So we have our movie clip, which is really the image sequence, being undistorted, meaning we've already calculated the lens distortion and it's basically inverting that. So now everything's nice and flat. We don't have any of that curvature. Then it goes into the scale node, which just makes sure that the footage is taking up the whole frame. So don't really worry about this node. So we have footage, it's being undistorted, and then this alpha over node is no longer needed because we got rid of the background render layers. We're going to plug this into here. So what's happening is, V to zoom out, what's happening is we have this undistorted background as this undistorted image sequence as the background in this alpha over, and then over that we put our foreground. And that goes into our viewer, which is what we're seeing in the composite. And of course, the reason we don't actually see our 3D objects is because we need a render. But before we do that, back to the layout. So you can see that this shadow is only trapped in the background layer. So we can actually delete this. So now everything's in the foreground, and we want to take this and put it in our foreground collection. And now we have everything in the same render layers and the same collection, and everything's good. So we can actually click X to delete this collection. So now everything should be working perfectly. So when we hit F12 to render, let's see what we get. So we're getting this render from the camera's point of view, which has our object, our shadow catcher, which is transparent except for the shadow. And hopefully we'll be done rendering soon. This is a good opportunity for me to get some water. Okay, so it's going to render through this, and then it's going to do another pass just to get the background. There we go. And you can see that it looks like our object, with the correct orientation and everything, is indeed in our scene, and this is the really cool part. So back in our compositing, we can see what's happening here. Again, we have our render layers, that's everything in the 3D viewport, is being put over the undistorted background image. And the reason you don't want to keep the distortion is once the object gets around the edges, it's going to look like it's drifting because of this curvature. So it is good to get rid of it. And since these are isolated, like I said, we can do a hue saturation value and mess with a bunch of stuff. So we can bring up the value, which will make everything brighter. As you can see, our monkey, our Suzanne, I'm trying to zoom in here. Our Suzanne is getting brighter. Of course, this is also affecting the shadow because we've put everything in the same render layer. So I'm just going to get rid of this, put this back here. And if we're happy with all this, we can get ready to render this into an image sequence. So I'm just going to enable a timeline here, just to make sure everything's tracked on correctly. And we're going to get a bit of glitchy movement, but that's just because Cycles is updating over and over and over again. Okay, so this is looking good. And before we render, I just want to make sure you have a couple things set so there are no issues. First of all, in the Render tab, like we've always talked about over and over and over again, make sure we're using standard mode, because we want our background images, when they're processed through this compositor, we don't want them to be turned into a filmic grade, essentially. We want it to look the same way that it looked like when we filmed it. Some other things is make sure this transparency enabled, or else your shadow catcher is going to be a solid object that still has the shadow, but you can't see through it. And then, of course, the obvious things, like in the Output tab, we can set this to be 30 frames per second. And I do want to render this quickly, so I'm going to make sure the samples are very low. So our render samples can be something like 2. Which is going to look very bad, but it's fine. We'll use GPU. And then we can render this as a movie. Again, this is just export settings. It's really not that important. So FFmpeg video is going to be a video file. Encoding, we'll use an MP4 because that's standard. It should be what you're watching this on YouTube with. It's an MP4 with, low quality, right? We're trying to make sure this is rendering as fast as possible. And once everything is set up, Control F12 to render the animation. And that is the speed I like. So maybe we'll render something like 20 frames, and hopefully we'll get a good, a long enough sample to tell if it's sticking on correctly. And I'll take this opportunity to talk about the plan for the future of the series. So this tutorial has already been going on for a while, maybe around an hour or so. So I don't think I'm going to do the other 2 camera tracks in this part. It's going to take forever. We have another shot with a wall and a floor. I kind of reversed those, a floor and a wall. And we also have the tripod shot that I was talking about. And again, we only changed the process a little for this. Our orientation is a little bit different. So I think I'm going to make a shorter part 4 that's just going to deal with doing these 2 examples, so maybe like a 20 or 30-minute video. And then beyond that, we still need to talk about object tracking and deformation tracking. And then I think we're done with everything we need to talk about with motion tracking in Blender. I know, it's sad. But, okay, so we have 50-something frames. That is way more than we need. And hopefully, if this is not corrupted, we should be able... Oh, you know what? You know what? I didn't set an output path. At least I did. It's in this temp folder, which means we need to find this temp folder to actually view our file. Do not make this mistake. Okay, so C temp... This is where everything gets loaded by default. Okay, so we can see our footage. And of course we have this grain because we have 2 render samples. So if we set this to repeat, we can see that this is tracking on very nicely. And we didn't even mess with the light that much, but the lighting already looks like it matches pretty well. You can see in these cars it's directly under, which means the sun is directly overhead. You can also see this with the bikers in the background. But if, let's say, you had a different scenario, again, this light is what affects the direction and softness of the shadow. So we could just bring this up and bring it directly over, and now our shadow is exactly under Suzanne. And if we go into the lighting options, again, make sure that you're in cycles to get some of these settings over here. Is the size, we can bring it up, which will give us a nice soft shadow. In this case, it's kind of hard to tell. It's a bit soft, maybe something like 0.5, and you can match your shadow. But I think I've been rambling a long time, a really long time about camera tracking for just one shot, but I wanted this to be very comprehensive. So hopefully you learned a lot about camera tracking in this video. There will be more motion tracking tutorials coming soon, and if you enjoyed it, I have a Patreon. You can support these high-quality tutorials. That's what I call them. I do think they're pretty good. You can support these tutorials over on that Patreon. If you feel like donating, you get benefits like behind-the-scenes content, and, you know, you basically learn things before everybody else. I'm like, oh, I'm going to make this video. You guys should know. I'll tell everybody else in 2 days. So if you're interested in supporting these videos, that's where you go. But hopefully you enjoyed this video. Again, I'm really sorry for all the stuttering that must have happened in the second half of this. Maybe I can edit some of it out, but we'll see. Can't edit that one out, but whatever. Hopefully you guys enjoyed, and I'll see you guys on the next one.